Okay. G'day everyone. Welcome to Aries workshop number 3 for Sem 2 2021. Today we're going to be talking about more CFD, computational fluid dynamics. And this is part 2. So part 1 was looking at space claim and building our geometry for our problem that we want to solve. And then today we'll be covering the fun part, which is building the mesh in Ansys Fluent and solving that mesh to hopefully create some pretty pictures of pressure distributions and path streamlines and stuff like that. So first of all, let's sort of review over what we did last week or the week before. We took our open rocket model, we made it in Onshape, and then we imported that into space claim. And we simplified it a bit before putting it into space claim. And we corrected the orientation so that gravity points down the rocket. We repaired the geometry a little bit using Ansys's built-in tools. We cleaned it up a bit and split it into 4 because it was a symmetric problem. Then we created this enclosure around the rocket, which included just the air around the rocket, not the actual rocket. And we created these things called bodies of influence, which are 3-dimensional bodies, which we want to define a specific mesh requirements within those areas. So in particular, we want to have a really fine mesh within these bodies of influence. So you can see there's a body of influence around the car where we would have a finer mesh. And then for the broader enclosure, we would have a more coarse mesh. And there's actually a second body of influence very close to the front left wheel. And that would be even finer. So we created those bodies of influence. And then what we did was we created name selections. And we wanted every face in our model, including the bodies of influence, to be included in one name selection. So we're sort of grouping them together, all of the faces, and we're grouping them by what boundary conditions we want to apply to them and what meshing conditions we want to apply to them. So for example, we group the body of influence faces together because we want a fine mesh in that body of influence. We group some curved parts together because we want to apply specific curvature conditions for the mesh on those curved surfaces. And we also group some small faces together because we want to apply a really fine mesh to those small faces to ensure that we capture what's going on those really tiny geometries. And then we had the inlet and the outlet and all of the walls surrounding the rocket. We grouped those by boundary conditions. So we had the symmetry planes and the inlet, the outlet, the wall. So that's where we're at. We finished everything in space claim. For those of you who wanted to use that document, you can go to the Aries GitHub, which is just this link up here. And if you scroll down, there's the rocket space claim file. Click on that, download it, and you should be good to, that's everything we did last workshop, so you can put that straight into Fluent. And of course, the recordings and everything is on the GitHub. The previous recording for everything we did in space claim is also on YouTube here, so you can catch up. And if you're wondering where you can get Ansys, if you just type in Ansys student, you'll find this page and click on the Ansys student package. You can download the 2021 Ansys student for free, and it includes Fluent and space claim and everything that you would need for free, which is really awesome. So let's assume we've done all that and we want to open Fluent. Now, it's a bit tricky opening Fluent in 2021 for some reason. It's not in this list in the start menu. So what you have to do is open Workbench, which should be right at the bottom. And we're going to use Workbench to outline our project. Workbench is like the top level project management aspect of Ansys. And what you could do is have a block for your space claim model and then have the info from that block feeding into a Fluent model or feeding into some sort of thermal analysis. You have all these blocks in a flow diagram, and I'll show you. So I'll drag a fluid flow, Fluent with Fluent Mesher block, Fluent meshing, drag that into our Workbench. And this is what I mean by the flow diagram. You can have a series of these. What we want to do is make sure we choose the one that says Fluent meshing, first of all. Go to Geometry, right-click Import Geometry, and just choose Rocket Enclosure .space claim document, okay? So once we've imported our space claim geometry into the Workbench, we can right-click on Mesh and click Edit. That's going to open up the Fluent Launcher window. Now, it's really important that you check the number of cores you're using down at the bottom here. For those of you who are using the student version of Ansys, there's a limit on the number of cores that you can use. You can only use 4 in total. So count these 2s as just 2. Don't count them as 2 plus 2. Just count them as 2. And also it includes the GPU. So my sum total is 3, 2 plus 1. If I went above 4, then that would cause issues. So for just to be safe, keep it at maybe 2 cores here and 1 GPU. And for those of you who are still having issues with the student version on your own computer, maybe you can't use enough nodes or can't use enough cores for the purpose that you want, try My Uni Apps on the Unimel website. It's a way of essentially logging into one of the computers that's sitting in the engineering building on campus, and you have access to all of the software that's available on one of those computers, but it's just through a server and it's on your screen. It's a bit laggy because it's through a server, but it has access to a whole bunch of software. So My Uni Apps is a great alternative if you can't get it working on your own computer. But anyway, if you've checked that you're not going over 4 cores in total, then you can press Start. And it's going to launch the Fluent Mesher window. Might take a little while to get started. So this entire window is just the meshing part of the Fluent. And at the very end, we're going to click this button on the top left, which will switch to the solution. So for now, if we go to our outline view tab, this will allow us to show all of our geometry and mesh in this, this 3D window. At the moment, we haven't got any geometry imported. So what we need to do is go to the workflow tab and go to this import geometry button. And click the 3 dots to select whatever file you want to import and press import geometry. It'll take a while, but it should import all of the geometry that you had from SpaceClaim. So what we're going to do to create our mesh is follow this set of steps here from top to bottom. And it's really easy. It's in the watertight geometry workflow. So there's a drop-down menu here where you can choose different workflows, but by default, the watertight geometry one should be selected. So after we import our geometry, we can have a look and we can see, you know, the enclosures there and the rockets there, and there's a few different bodies of influence that are there as well. If we want to view different elements of it, we can go to this geometry objects list and right-click draw, and that'll draw just the element that you've right-clicked, that you've selected. So this is just the enclosure. You can see there's a hole where the rocket should be. If we wanted to just look at the nearby body of influence, we could select these 2 objects, right-click draw, and it will draw both of those. And if we only wanted to look at the rocket itself, we could go inside this enclosure and we could select the nose, fins, and body of the rocket. Right-click draw. We'll also click face edges. This will show you the edges of the geometry that we've imported from SpaceClaim. And this is what our mesh is going to try and replicate. This is the true geometry that we've imported. And the mesh is going to try and go as close as possible as it can to this geometry. All right, so let's add some local sizing. So what this means is in certain areas of our geometry, we're going to put specific sizing for that specific area. And for other areas, we're going to have a larger sizing. So global sizing is it's applied to the entire geometry. It might be 50 millimeters across, might be the size of your elements. And then the local sizing is like, okay, I want you to put aside the global sizing. I want you to look at this specific area and I want to apply a finer mesh to that particular area. For example, at the nose, we might want some local sizing, whereas out here in the purple region, we would have just global sizing because it doesn't need to be fine. Hopefully that's clear to everyone. So let's go to our PowerPoint and just run through to local mesh sizing. So all you need to do is select yes, and we're going to choose the local sizing for our bodies of influence first of all. So let's go name body of influence near. Growth rate is always 1.2. That's just a standard value that you can apply to all of your local sizings here. And then there's different types of local sizing that we'll see. So let's go into Fluent, add our local sizing called body of influence near. Oh, my keyboard is playing up there. Right. We want to select a body of influence type. Target mesh size should be 20 millimeters. Okay, so let's add a ruler. Speaking of millimeters, if we go to this option here, which we can click on, it will give us a ruler. Okay, and that's in meters. All right, so what it's saying is our enclosure is roughly 2 meters long, and our rocket is, well, roughly 35 centimeters long or something. So that tells us we've got the right scale, which is good. And this is specifying a value for the target mesh size that we want for that area. And then select by tells us what area do we want to apply that mesh size to. And if we look at our PDF here, we select by label and we just go body of influence near. And that's the body that it's going to apply that local meshing to. Let's change this. I think we're in the wrong units here. So let's go 20 mil and see what happens then. Okay, yep. So what happened there was I had 20 selected as our mesh size, but I should put it into meters instead of millimeters. So 0.02 meters is 20 mil. So that's the size, those bright green squares, that's the size of the mesh approximately that we're going to have in that area. All right. So in this case, I've put 20 there, but that's 20 mil. And in this file, we've got it in meters. So that's why I've done 0.02. All right. So we've added that. Now we'll add a body of influence for the far body of influence. Sorry, we'll add a local sizing for the far body of influence. So again, just go local sizing, body of influence. And for this one, let's say we want that to be 50 mil. And we just select body of influence far. Again, we can go over here and we can draw our far body of influence. And it's saying, okay, that's the size of our mesh for the far body of influence. If we think maybe that's a little bit too coarse, we can say, all right, 30. And we're quite happy with that. And then we just press add local sizing. So that's the local sizing for the body of influence far. And let's add a local sizing now for the curved surfaces. So there's a different type of mesh restraint that you can apply for curved surfaces. So we've got local minimum size, max size, and curvature normal angle. So this curvature normal angle is the maximum angle between two elements of our mesh. And that allows us to say, all right, we've got a curved surface. We don't want it to just convert that curved surface into a 45 or 90 degree angle. We want it to have a maximum of 9 degrees between those elements. So it's a nice curved surface. So on top of allocating a specific size, we can also allocate normal angle. And again, we're going to have to convert this to meters instead of millimeters because we've got different units here. Let's go. So let's just call this body curve. And we'll go to curvature as our option. We want the minimum size to be 0.1 millimeters here. So that's 1 millimeter and that's 0.1 millimeters. And the max size to be 3 millimeters. And we want that curvature angle to be 9. And we want to select the faces on the body. All right, so let's go to body. Let's look at what other curved surfaces we might have here. We can right click on that, draw that. You can see, okay, that's the surface that we're applying this curvature thing to. And that's the size of the mesh. I'm pretty happy with that. So we'll add local sizing. Now we want to perform another one for the nose, because that's also a curved surface. So I'll say nose curve. Again, it's a curvature restraint. We want that to be, well, the nose is a bit more, the nose is a bit finer. If I right click and draw the nose, it's got some finer geometry towards the end. So I might want a smaller mesh there. So maybe I'll say instead of 3, I might say 2 millimeters for this. And I'll say 9 degrees between the elements. That should be fine. We can see our mesh that we're going to be applying to the nose, or an approximation of the size. So we're all good for the curved surfaces now. Next, we can go to tiny faces. So there are some tiny faces on the edges of the fins. And if we don't create a really fine mesh that fits at least one element across this face, then we're not going to be able to capture the changes in pressure, the changes in velocity across that tiny face. And the solution will probably explode. So what we want to do is create a proximity local sizing at that area. So what we'll do is fins prox, go to proximity, and this means anything within the proximity of this these tiny areas will need to be small. So let's see what sizes we selected here. We had a min size of 0.1 mil and a max size of 0.2 mil and 3 cells per gap, which means we want to try and achieve 3 cells across that tiny face. All right. So that's 0.1. The max size will be 0.3. And we want 3 cells per gap. And we want to apply that to the fin edges. And that should have been 0.2. Sorry, we go to faces and fin edges. So let's draw that. Okay, so these tiny faces on the edges of the fins are now going to have the right mesh size. And the boxes, there's a tiny box over there. Okay, so that's the kind of mesh scale that we're looking at near those edges. Do add local sizing. Very good. All right. So that's all we need to do for the local sizing. We had the bodies of influence needed to be slightly smaller mesh, and the curved surfaces, you wanted to set that minimum, the maximum angle between the elements, and the tiny faces, you want to make sure they have a really small mesh there. And that's called proximity. Next, we're going to generate this surface mesh. And this is more like our global settings. So you can see we go from 1 to 50 millimeters. Our growth rate is still 1.2. And our size functions, curvature and proximity. What this says is it tries to capture the curvature and tiny faces of the surface, okay? And those are the local sizing requirements that we set earlier. So you want to make sure that's on. And you can set curvature normal angle to 9, as we said before, and the cells per gap to 3, which is what we used for the tiny faces. So just in case we missed any curved surfaces or tiny faces, that's going to try and sort that out as well. And you want to scope it to the faces and the edges. So again, let's go to the next step. So generate the surface mesh. We want that to be 1 mil up to, what was our maximum size? I think it was 50. Remember, we're converting everything to meters when I fill this out. All right, curvature and proximity. Normal angle, we want it to be 9 degrees between elements. We want 3 elements, if possible, across each gap. And we want to apply that to faces and edges. And if we want to see what that looks like against the entire enclosure, we can draw that. And let's see. We've updated the sizing so that it shows where the square's gone. There we go. Those are the size boxes. So that's the kind of mesh size that we're looking at. There should be some really tiny ones as well, which show you the minimum size. So that's this tiny little cube here. And then obviously the larger one is the max size. And maybe you think, that's probably big. That's probably can go a bit bigger than that. So, because we don't expect the pressure distribution or the velocity distribution to change dramatically across this blue face. So we don't need to put too many meshing elements across there. So probably this size is going to be more than adequate. And remember, the smaller you make your mesh, the slower it's going to be to get results. And if you want to keep solving for different iterations of your design, that can get really important. You want to minimize the time that your computer has to spend calculating this stuff. So you really want to create the largest mesh that you can reasonably capture the physics of what's going on in the situation. Okay, so remember that each element is essentially a linear interpolation of that function that might be pressure, it might be velocity, it might be temperature. each element is creating a straight line interpolation from corner to corner. So you need to ask yourself, do I think the pressure is going to be approximately a straight line? If I drew a straight line from the corner of this red square to the corner of this red square, is that going to be close to the physical pressure distribution? If I think the pressure distribution is going to be really wavy and full of lots of tiny oscillations that I want to capture, then this mesh size needs to go down to capture those oscillations. And I need to reduce the size of the mesh to the point that I could draw straight lines and it would closely match the actual curve. Hopefully that makes sense to people. Maybe I can annotate. So let's say X is our location in this direction. That's X, just as a very rough explanation of what I'm saying. And say this is our pressure. Say we think our pressure looks like this. Each element is going to be a straight line. So this element might say, all right, it's going to be like that. And then you have another element that's 50 millimeters across that might do a straight line like this. And another one might do a straight line like that. Now, in this case, you can see that it's probably not ideal up here because our pressure is changing quite dramatically in a small space. However, for this region here, where the pressure is not really changing over 50 millimeters, it is a pretty accurate representation. So maybe for this area where it's curving, we might want to try smaller elements, something like elements like this size, and that'll fit to that curve quite nicely. So that's a crash course in how to select your mesh size. And I think this is going to be more than adequate. So I'm happy with that. And I'm going to generate the surface mesh. We'll take a little bit of time. Let's check out the PDF in the meantime. Should come up with this. And you should be able to see when you've generated your mesh, should be able to see the sizing. Okay, so our sizing is, you know, roughly what that red box was before when we're away from the rocket. And we should, closer to the rocket, we've got that outer body of influence, which I can draw. Okay, so that there, if we want to compare that to, let's draw them both at the same time. Oh, I can't, never mind. It's not letting me draw multiple things at once. Ah, there it is. Okay, beautiful. So you can see that by the time we get into this body of influence, the mesh has reduced its size to what we specified. And even closer to the rocket, once again, I'll just draw the mesh itself. Even closer to the rocket, you can see the mesh gets finer again. You can see that this curvature of this dark blue surface has been captured. And you'd find that the maximum angle between any of these dark blue elements and in fact any of these nose elements would be 9 degrees. What option do we need to view the mesh? I'm just getting solid colors. So make sure in the display options, you've got all of these options ticked: face edges, free faces. Might be something like that. If I remove that, you just get a solid block like that. So tick face edges and right click on your mesh object and press draw, and it should show your mesh like this. That was just a question from the chat. Okay, now we can also zoom right in on these tiny edges and you can see, okay, that's worked nicely. I've got nice and square elements across here. They're not really warped rectangles or anything. The more warped they are, the less accurate your solution is going to be, and the more prone to explosions in your solutions you are. So that's why we had to specify that, you know, our mesh is really small here so that we have squares here, or triangles that are close to equilateral. They aren't too severely warped. So right near our fins, all of our local sizing seems to be working well. So that's a good sign. Okay, so this is just the surface mesh. This isn't actually the three-dimensional mesh throughout the entire space. This is just on the surfaces. So what we want to do next is create the actual three-dimensional mesh. So let's go through the steps. Oh yeah, I can also, I should mention that if you found there were some issues with your mesh and you weren't happy with the sizing, you can just right-click on your mesh object, delete it, including edges and faces, and then add some more local sizing or edit the local sizing to fix any of the issues that you had, and then just remesh the surface. Okay, so it's a good idea to check the quality of your surface mesh before running through with the rest of the simulation. So what we want is a minimal number of skewed surfaces, skewed faces. As I was saying, elements should be close to square or close to equilateral if they're triangles. The more warped they are, the more long and skinny they are, the worse the results are going to be. So we're going to right click on this mesh object in the outline view. We're going to click summary. And what it's going to do is it's going to give us a summary in this console at the bottom here. This is where you'll get a lot of information towards the end of this workshop. So you can see here our skewed faces is 0 and our maximum skewed is 0.56, which is pretty regular. I mean, really, it's only an issue once you're getting above 0.85. And it's told us that we have 44,000 faces in total. So it's always just good to double check that. If you did have lots of skewed faces, you would need to try and locate them. There are certain tools for locating skewed faces, which I won't get into today because that would take a while, but there's a way to highlight your worst faces in red, and then you can go through those and say, oh, I need to change the mesh size for those areas. And once you've got a good quality mesh that doesn't have skewed faces, then you can move on to the next step. We're describing our geometry. This step's really easy. We just say it consists of fluid regions with no voids because it's just the air that we're modeling. We're not modeling any solids because we removed the solids last workshop. We didn't include the actual rocket solid itself, just the air around it. So we can say just fluid regions, and those options can both be no. So let's do that. We go to the workflow, describe geometry, fluid regions with no voids. Just click describe geometry. Okay, now we're on to our boundary conditions. And boundary conditions are just as important as your mesh conditions. So it's really important that you get these right as well. These are crucial for allowing our solution to initiate. So let's look at these various selections that we made last workshop. And this is where it really comes in handy that we made those name selections earlier on. We've grouped all of these faces in terms of what boundary conditions we might want to apply. So for example, the body of the rocket, we just want to treat that as a wall. We just want to treat it as a brick wall that nothing can flow through. And we just hit wall, that's all good. Same with the fin edges and the fin faces. They're also just a solid that we don't want anything to flow through, so we can just put wall. For the inlet, we want it to be a velocity inlet. So the air is going to be flowing at a particular velocity in here. And the nose, that's just part of the rocket, so we can say that's a wall. The outlet is at the rear here, and we want that to be a pressure outlet. We use velocity inlet and pressure outlet. Just a little detail that you need to keep in mind. Then we have a really interesting boundary condition is the symmetry boundary condition. So you can see that the faces in yellow are going to be treated as symmetric. So this is only solving a quarter of the rocket, and we're just going to apply symmetry around the other 3/4 at these faces. Okay, so that's what symmetry is. And for the wall, that means the 2 faces that are furthest from the rocket. So these green faces here are on the opposite side to the actual rocket, which is on the purple side. And we just want to treat that as a wall as well. So we don't want any air to flow through those. Again, you can go to your outline view and right click any of these zones. They'll be under your enclosure. If I wanted to see what the wall looks like, I'll just draw that and that'll show just the green faces. All right, so that's what we're treating as our wall. If I wanted to see the symmetry plane, I'd right click on that. Okay, those are what our symmetry planes look like. All right, so just update the boundary conditions. And all we've done is select the type of boundary conditions we want to apply at different faces. And then we want to update our regions. This is very easy. It's just one enclosure, which is full of fluid. So that is done. And then we want to add boundary layers. So for our 3-dimensional mesh, because this is a fluids problem, we're going to have fluids that are flowing very close to the rocket, right? But for those of you who've studied fluid mechanics or fluid dynamics, you would know that really close to the surface of this rocket, the velocity is going to approach 0. And there's going to be this boundary layer where the velocity goes from 0 at the surface of the rocket to the free stream velocity, which is just the velocity of the air. But there's a transition region. So we're going to add some 3-dimensional elements that capture that, because you need to add a lot of really small elements near the surface. And we haven't specified that yet, because that's part of the 3-dimensional mesh. So we're going to add boundary layers. We want to add smooth transition boundary layers, which is what I was just mentioning before. You can leave all those values, just put the number of layers as 5 instead of 3. And we'll see what that looks like once we've made the volumetric mesh, i.e. the 3-dimensional mesh. So everything up to this point was just the surface mesh. Now we'll make the 3D volumetric mesh. We're going to use Polyhex core as the algorithm that's going to select what types of 3-dimensional elements we're going to use for the mesh. So there's various different shapes of FEA elements. There's hexahedra, which are just cubes, and there's tetrahedra, which are just triangular pyramids. And there's also polyhedra, which are something like a soccer ball, and they have a lot more faces. Polyhex core will use hexahedra when it wants to create a finer, more structured mesh, and then further away from the rocket, where it doesn't need to be as structured or as fine, it will use the soccer ball shaped polyhedra thing. So we just need to select generate the volume mesh, fill with polyhex core, and the maximum cell length is, well, we've said 25.6 here. But again, remembering, oh yeah, add boundary layers. Again, remembering that we need to correct the units. So what did we have? Max cell length 25.6. So that would be 25.6 millimeters. And I think all we need to do then is click generate the volumetric mesh. Let's draw the 3D mesh and see how it looks. So now we're creating the mesh across the entire field. And it will take a little while. It won't let you do much while it's generating. But the idea is we'll be able to see these really fine rectangles near the surface of the rocket. And those are our boundary layer prisms. So these really flat sort of slabs are called prism elements, and they're used to capture the boundary layer, which is that transition from 0 to free stream velocity. All right, cool. So you can see here that we've created our 3D mesh now. And what we can actually do is we can select where we want to view that by sliding this red arrow. And you can see the bottom right-hand corner, we've got our X, Y, and Z axes. If we want to change the way that we slice this, we can limit it in X, for example, and that'll allow us to slide in the X direction instead. So if we wanted to get sort of a cross section of what it looks like near the rocket. So let's zoom in and get really close to where the rocket is. So this is what our 3D mesh actually looks like. You can see there's these sort of bubbly soccer type things far away from the rocket. And then closer to the rocket, where we had that body of influence, it starts to get more into these hexahedra, which is more regular and structured. And you can see the mesh gets finer and finer as we get towards the fins. And if we go right onto the fins, hopefully we can see that it gets really fine. And if we go near the nose, you can see these sort of slate prisms here, which represent the boundary layer. So there we go. We've got our first of many pretty pictures to look at. I think this is one of my favorite parts, where you get to slide through this cross section of this really complicated geometric surface. So yeah, feel free to toy around with that. Maybe you want to do a cross section of your rocket like this. And you should just double check that all of your elements are doing what you expect, and that you've got fine geometry where you expect it, and you're capturing your boundary layers and all that stuff. So yeah, that's very good. We're really happy with that mesh. All right, so we've done the full mesh and we're ready to go into solving. So we're going to switch to the solution window. It's going to warn you, are you sure your mesh is good? We're pretty happy with the mesh we've got, so let's just go. So once we've opened our Fluent solver, there'll be 4 tabs that we want to look at: the domain tab, the physics tab, solution tab, and the results tab. We don't need to look at the user defined tab because we're just starting out. So click the switch to solution button, and this window should eventually come up. If you're having issues, just remember what we mentioned at the start of the video about not going over the maximum number of cores. First thing we want to do in the display tab is we want to check our mesh, and we also want to check that it doesn't give us any errors. We could also check the quality, but we already checked the quality previously, so it should be good. Just perform mesh check. It's not showing us on the screen yet, but we have actually brought our mesh in. Okay, so it's checked the mesh for us. And there's no errors coming up, so we're all good with that. Then that's actually all we need to do. In the domain tab, we can go to the physics tab, and we want to put gravity in. Okay, so physics, click the general settings here. That will bring up this task window. And we want to apply the following settings: pressure-based, absolute, steady, and we want to tick gravity. Pressure-based, absolute, steady, tick gravity. Gravity is going to be 9.81 meters per second squared in the Z direction, which, if you'll remember, we pointed down our rocket from the nose. So that's all good. We don't need to make that negative because it's already pointing down the rocket. Beautiful. Then in our physics tab, we want to select the model that we're going to use to model the viscosity and the turbulence of the fluid. So click on this viscous button, which is at the top here in blue. It's going to bring up a whole bunch of different options. Don't worry. All you need to do is select K omega SST. There's a whole bunch of different models that you can look into, but K omega SST is just a reliable, robust model that is strong when it comes to solving turbulent flow. So this is going to be able to simulate some eddies and turbulent behavior in our fluid. And that's all we need to do for that. If you want to dig deep into that, feel free. Then we go to boundaries, and this is where we're going to actually set the values for our boundary conditions, give a bit more info. So in the physics tab, hit boundaries. Now, we want to go down this list one by one, and we want to make sure we've got the right values. So for the body of the rocket, we want to hit edit. We know it's a wall, but there are a few different options for walls that you can model in Ansys. We want it to be a stationary wall. And you can also hit roughness height if you wanted to. So I think the roughness that you get in open rockets is, there's a couple of different options, but the standard roughness is 60 micrometers. So you can just hit 60E -6. And that's going to apply 60 micrometers of roughness. You could leave that as 0 if you wanted to just model a perfectly smooth rocket, but that's always an option for you. Fin edges, you'll remember, is those tiny faces on the edges of the fins. We want that to be a stationary wall as well because the flow is not moving there. And we'll set our roughness again. Fin faces. Same again. Just setting that roughness. And double checking once we've entered it. Then we get to the inlet. That's a velocity inlet, but there's a couple of options for that. What way do we want the velocity to go? How much velocity do we want? So for the sake of this workshop, I'll keep it nice and low velocity because the higher the velocity goes, the more difficult it is for the computer to process. We'll just keep it to 10 meters per second for now. Typically, your rocket's going to be traveling a lot quicker than that, but it's fine for now. And that's all good. It's going to automatically create a normal vector to that inlet, pointing inwards to the enclosure. And it's going to be going at 10 meters per second. If we wanted it to point in a different direction, we could change that to -10, but we just want that to be 10. The nose, again, that's a solid wall. And we'll set the roughness to 60 micrometers. And it's a stationary wall. You'll notice I skipped this zone that says enclosure. If you've got something with a long name, just ignore it. You don't need to mess around with that one. All we're concerned with is the ones that we were looking at. For the outlet, we want it to be a pressure outlet. And I'm pretty sure we want the gauge pressure to be 0 at the outlet. I'll just double check with what we selected here. Oh, maybe I didn't specify. Well, we'll just set the gauge pressure to 0, which means we're atmospheric pressure at the outlet. 101.325 pascals. The symmetry boundary condition doesn't have any options, so that's all good. And then this outer wall, the outer wall is actually moving with the air. So this is not a stationary wall. We're imagining that our rocket is sort of moving through this tunnel, which has air moving at 10 meters per second. So relative to the rocket, the walls are moving at the same velocity as the air. So if I go to the PDF, it'll actually talk about that. So the wall velocity has to be the same as the inlet, and that's 10 meters per second in the Z direction. So you go moving wall, 10 meters per second, set X and Y to 0 and Z to 1. This just specifies a vector for the direction. Okay, so we've set up the actual values for our boundary conditions now, such as roughness and velocity and stuff like that. Now we can move to the solution tab. And this is where we can start to select what we want to actually solve for. And what we want to do in this case, for example, is solve for the drag coefficient on the rocket. And I'm going to go to the solution tab. You go definitions, new, surface report, volume report, whatever you would want to report, okay? So we want to report a force drag, all right? And then we want to go drag coefficient in that window that comes up and select the actual faces that we want to compute the drag on, which is just the rocket faces itself. And we also want to calculate the direction in which we're measuring the drag coefficient, which will be in the Z direction. So let's go to force report drag. Yeah, there's a whole bunch of different options here. You can find the area, you can find the volume of stuff, you can find the mass of certain areas, you can find moments and forces. We're going to select those four. We're going to go Z direction for our drag coefficient. Report, I'm going to rename that to report CD. Press OK. And what that's going to say is, all right, when we run our solution, it's going to give us, that's what it's going to calculate. Next, we can go to initialize. It's very important that you initialize first of all, before you try and run the calculation. That's just going to give us the 10 meters per second everywhere. It takes a little while to initialize. While that's going, we want to set our timescale factor to 1 and the number of iterations to 200. If you want to mess around with those, you can, but typically it's going to converge within 100 to 150 iterations, so 200 should be plenty. Thing is, once it converges, it'll actually automatically stop. So you don't have to be worried that it's doing 50 iterations it doesn't need to do. It's going to automatically stop. And then we can hit calculate. So number of iterations, 200. And we can hit calculate. All right, so if you're in the student version of Ansys, you can only designate a certain number of cores. So this might take quite a while. But what you want to look at is your residuals. So the residuals indicate an estimation of the magnitude of the error for the velocity distribution and also a couple of other things. It's saying, all right, we want to keep iterating until our residuals, i.e. the estimation of our error, reach a certain value. And typically you want to see these lines going down by a factor of 10 to the 3. So we'd want to go from this marker at the top for black, we'd want it to go down to 3 lower. And for this blue line, we'd want it to go from -4 to roughly -7. If you're seeing these residuals go crazy, then you know something's wrong with your mesh and your solution is exploding. So at the moment, we're looking really good. We're going down. And you'll notice we built that report, and the report is giving us the drag coefficient value. And it'll oscillate around a bit. It'll go up, it'll go down, and hopefully by the time the residuals have hit a small enough value, your CD value should be pretty accurate. So we'll leave that to calculate away. Yeah, we want the residuals to decrease by a factor of 10 to the 3 and stabilize for a convergent solution. So if you have a nice flat region there, then you know your solution is not exploding, it's not going crazy anywhere. And once you get to the end, it will actually list in the console the value that it got as the final value for your drag coefficient. So when I initially ran this, I got 0.013. Is that a realistic drag coefficient? Probably not, because it's finished. This probably isn't a realistic drag value, because when I calculated this, I can then compare that to standard drag coefficients that you can find on the internet for spheres and stuff like that. So, for example, let's see what we get for the drag coefficient of a cylinder. There are a bunch of standard values that you should expect, okay? So for a streamlined body with very aerodynamic geometry, you can expect a value around 0.05. But for bluff bodies like this, it's going to go up to around about 1. So I would say this solution here that I got is not accurate. So there would have been something wrong with the mesh when I initially did this. And also I hadn't put the roughness values in. So that's a good check to say, okay, I've got this value out of my CFD, but does it make sense? Before you go and run on to your project managers and say, oh, the drag value is really low for our rocket. Think about, is that realistic? Okay, so what did we get here? We got 0.03. It's a bit higher because I added the roughness, but it's still very low compared to these standards. For a streamlined body, it should be 0.04. We're getting 0.034. So you could probably say that it's underestimating the drag. Now, is that because our velocity is too low? Should we try it with a high velocity? You know, think about these kinds of variables before you run with your solution. Do we need to refine our mesh further, closer to our nose, to the body? What's going on? So try a couple of things and see what different values you get. But this is definitely closer now that we added the roughness. Now, what we can do is calculate some forces, some moments. Maybe we want to find the center of pressure. So in Open Rocket, we got a center of pressure value of 29.4 centimeters from the nose. Let's see what we get here. We go to forces and force reports, center of pressure. At the bottom, where is it? We go to results, reports, forces, center of pressure. We want it to be in the X direction, and we want it to be for those four surfaces that define the actual body of the rocket. We print that. This will give us the center of pressure coordinates. Okay, so we're getting at X is equal to 0, the center of pressure is 0.259 meters along the nose, from the nose along the body of the rocket. So 25.9 centimeters compared to, we got 29.4 here. So it's close, but it's definitely not exactly what Open Rocket got. Again, remember, Open Rocket is calculating this at Mach 0.3. We calculated it at 10 meters per second. So that's going to significantly change your results. So think about what kind of velocities Open Rocket is using. I'd run this calculation again with a higher velocity if I had time, and I'd see what kind of location we're getting then. Okay, so that's a nice sanity check again. Is your software giving you consistent results with other software? And now we can try the fun part, which is all the cool visuals, path lines, and stuff like that. So let's have a mess around with that. If you go to the bottom here, you can go to graphics, contours, and we might want to plot contours of pressure. Let's say static pressure. And what do we want to plot those on? Well, we want to plot them on the rocket itself and the symmetry plane. And it's going to display them. Oops, I forgot the nose. And this is the static pressure. Now you can see that the static pressure right near the tip of the nose is a lot higher than everywhere else. And right here on the fins, we've got some crazy gradients happening. Okay, so maybe we need to refine that even further because the gradient of the pressure is very large near the edges of the fins. All right, so we could go, okay, we need to refine the mesh in this area a little bit more. And, you know, put your engineering hat on, think about, does that make sense? Well, it makes sense that we would have higher pressure on this front face because the dynamic pressure of the wind hitting that front face is going to make it increase. So use that kind of logic to think about, okay, what you can also do is you can remove this auto range feature and you could set your own range that you might want to test. We could plot the dynamic pressure. All right, so we can see the dynamic pressure is all acting on the body of the rocket, but it's very low. And then it's a lot higher. And the reason it's very low here is because the velocity is very low on the body of the rocket because of those boundary layers. So that's actually a good sign that our dynamic pressure is low. And you can also see that behind the rocket, there's this wake region where the velocity is going to be slower, which means the dynamic pressure is going to be lower. Let's say we want to plot the velocity magnitude. Well, this confirms what we said just before about the dynamic pressure. The velocity is highest when we're away from the rocket and we're at the wall. And you can actually see that it's roughly at 9.34 meters per second, which is about 10 meters per second, which is what we expect it to be. It's between 9.34 and 10.5 meters per second. And it's basically 0 meters per second on the body of the rocket, which is beautiful. Okay, so that's confirming, you know, our simulation makes sense. We're getting all the stuff that we would expect. We're getting this wake region. Cool. And then we can do stuff like path lines. This is probably my favorite feature. Let's say we want to do path lines, which is just putting a bunch of particles into your 3D space and then following them, how they travel along the body. So we might want to put a bunch of particles near the rocket and on the symmetry plane. And let's see what happens. Oh, maybe I missed something. Or maybe it's just taking a long time to solve. Again, on the student version, you only have limited computing power. And hey, we can see, okay, it's definitely following these particles, but it looks like it's following them for a very long distance. So let's reduce the number of steps to 100 and remove the symmetry plane and display that. Wait for that to load. So this will allow us to see the turbulence, the actual shape of the turbulence in the wake region. We'll see the curvature of the path lines behind the motor, and we'll see the eddies that can be appearing around the rocket. So you can see right under here, that's the curvature. So if you wanted to create something that's more aerodynamic, you could try and reduce the magnitude of those. And you can also see we can color them based on velocity as well. So maybe I should have done that. Or we could color them based on pressure, color them based on turbulent kinetic energy. And that'll give you a really clear visual of how much turbulence you have in certain regions. Okay, so we can see here, we've got the highest turbulence immediately behind the rocket, and on the actual surface, there's no turbulence because nothing's happening. We've got a lot of turbulence near the edges of the fins, and obviously away from the rocket, not much turbulence at all. So yeah, those are some pretty cool things that you can mess around with. There's also vectors, which will create like a three-dimensional vector field of the velocity. So let's display that. So this can give you another really intuitive view of how your flow is going around the rocket. You can see that it's flowing quite uniformly until it hits the edge of the fin, and then it's going all over the place. So if you've got, as I said, a lot of sharp changes in this kind of velocity field, you need to ask yourself, do I need to refine this further? Is this accurate enough? And you can see the vectors are really short on the body of the rocket because there's very little velocity. So yeah, that pretty much sums up everything that I wanted to show you for CFD. Thanks so much for watching. We've got one more workshop coming up, which will be on FEA in Ansys. That'll be in 2 weeks' time. And then that'll be it. That'll be all the workshops for this year finished. So hopefully we'll be seeing you all there for that one. And thanks so much for watching. This is all going to go up on YouTube. So if you have any questions, feel free to chuck them in the comments on YouTube and I'll do my best to answer them. But yeah, thanks for coming. Cheers. Bye.